but I hope that is something which you can continue doing, and probably if there is a requirement, then some other time we can do it as a tutorial. But today what I will try to discuss is a kind of a formal discussion on what we call as postulates of quantum mechanics. Now I believe that these postulates of quantum mechanics will make more sense because we had sufficient discussion on the experiments, and some of the issues of the experiments is a little bit well understood by now. So I hope the postulates will become more clear. So to start with, we have a quantum system. Okay, so a quantum system can be it can be a photon or electron or a particle with dual nature. Okay, so we called, I said there is a wave given by Eddington called wavicle. It has not become famous, but nowadays people also use some other name called quantum. It is also not very famous, but something which has a dual nature is what is called a quantum. It is, in the olden days this name was there. Now some people are trying to use this kind of name. It is not that it is a system, or you can also have a collection of them, a collection of electrons or photons and electrons together, etc., etc. These are all quantum systems. Now, one of the important aspects is that the behavior of these systems, the behavior or properties of quantum systems are not accessible to human experience, human observation or experience. We have to come to terms with this. Okay, it's not your or my observation, the complete human experience or observation. Because of this, the scientific approach is that of inference. We observe something and then infer something. So this inference is what drives the formulation. Okay, so when we say we are talking about postulates, that means once we write down the postulates, then we are not going to question them, because these postulates are kind of the best work that we can do based on all our collective experience. Okay, so we observe certain manifestations of these systems, how they manifest in different experiments, and then from there we try to abstract out the uh, rules. This systems might be governing. Okay, so that is what the rule book is all about. So postulates are basically the rule book. Okay, so now let us for formulation, for the formulation aspect. So let us consider the system to be a single particle. I will call it particle, but whenever I say a quantum particle, it also has a wave nature. Okay, it's a single particle. So this is my system as far as it can be a single photon, or it can be a single electron, or it can be a single proton. So some single particle. Now we can ask a question that what should be its state? Okay, so what is the state of the particle? State of the system. Now, in classical mechanics, we say that if you ask this question says that you have Q comma P. Okay, so this Q can be 3 coordinates and 3 momenta. Q comma P is the state. Okay, so you fix position and momentum of the particle, that will describe the state. Now, what can we do in quantum mechanics? Because in quantum mechanics, there is a wave nature. Okay, so here, due to wave nature, the state is described by a complex valued function. A complex valued function psi of r comma t. R and t are real, but psi is complex. That is why this is called a complex valued function. Okay, and what is this function? So this psi of rt, it is called the wave function. It's called the wave function. Because any wave will have some finite, it will occupy some space, and its shape will change from time to time. So a function of r and t are required. Okay. Now one can ask a question, what kind of, so it is a wave function. Okay, so the next question is, what kind of a wave is it? What kind of a wave? Because we are already familiar with certain waves, right? We know water waves, we know sound waves, we know waves on a string, we know uh, electromagnetic waves. Classically, we know different types of waves. Now you ask a question, what kind of a wave it is? Okay, so this is where people did not get a clear picture as to what kind of a wave it is. Okay, so it had to wait till Max Born had made a he has suggested that this psi, what kind of a wave? The answer given by Max Born is that it is a probability wave. It's a probability wave. Why this is called a probability wave? Because Max Born suggested that psi of r comma t, since this is a complex number, modulus square of d3r. d3r is a small volume around r. This has an interpretation that this is probability that a particle is found in volume d3 of r around a point r at time t. Okay, this is the probability that a particle is found in volume d3r around r at time t. Now, this is the probability. So in this language, modulus psi of r comma t, the square, is called probability density. Probability density. This is called probability density. Now, in this language, your psi of r comma t, which we called as wave function earlier, is also called probability amplitude. Probability amplitude. Okay, psi of rt is called probability amplitude. Okay, so this is your postulate number one. Postulate number one talks about what is the state and what does this state mean physically. So this is the first postulate.
Sir?
Yes.
Here I want to ask something. Sir, when we say the de Broglie wavelength is the spatial extension of the particle where the probability of finding the particle is non-zero, right?
Yes.
Now, when we come to this probability wave function, whether is it physical or is it related to that de Broglie wavelength? Is there any connection between those two?
When you look at this mod size square and the
Yes,
region over which that is non-zero,
yes.
that is of the order of de Broglie.
So this is something physical quantity, right?
Mod size square is, yes. Mod size square is the extent over which the mod size square is non-zero is physical. That is what we say that it has. Sometimes we say that it is a quantum volume of the particle.
Oh, so that lambda q is related to psi mod square.
Yes.
Means yes.
Yeah, that's true.
So that is physical.
Correct. Because if let's say another particle is coming within that overlapping within that volume,
Sir.
then some those two particles will cease to be different. They become identical particles. You
Yes,
will
sir.
not be able to say within that where which particle is.
Yes.
Okay.
Okay.
Yeah. So that is what this is. So this is basically the first postulate. Now let's try to understand.
Excuse me, sir.
Yes, I could not
Hello,
hear.
sir.
Ah,
Sir,
you.
I have
Go
one
ahead.
doubt, sir. The probability wave is look like a standing wave, sir.
Probability. See, how does this probability wave look like? There is no general. So in some problems it may look like standing wave. In some problems it may look like a running wave. So there is no strict rule that it should look like standing wave. Okay. So for example, if you take a bound state of any potential, okay, so it may look like a standing wave, but it is not a general rule that it should always look like a standing wave.
Sir,
Yes, sir. Thank you, sir.
Yeah.
this probability wave, is it a pure mathematical artifact, or in some case it can be physical also? That not the density, sir. That probability wave means psi of RT.
Yeah. So so that is why I want you to look at my first statement carefully.
Yes, sir.
So I think this statement is something which I have written down here. The scientific approach is that of inference.
Yes, sir.
Okay, so we don't know how does this probability wave look like.
Yes,
So
sir.
this is inference. That means I am making this statement so that it doesn't disturb any of my observations.
Oh.
Okay, all observations are fitting well. But now what this probability wave means? Okay, so what this probability wave means? So if you ask that question, then it is like your guess is as good as my guess. Correct? So just let me just argue something like this. Let's say that I have some 0 to some a. Okay, let's say particle is only between these with these 2 points, and let's say that this is how some. Sorry, I think I should not. Okay, so let's say this is how my probability looks like. Okay. Now, what I am observing is that the probability of finding, or the probability density, or probability of finding particle in some small bins around every point is actually oscillating. It is maximum at these points, and it is minimum at the other points, right? It's minimum at these points, and it is oscillating between maximum and minimum. So I might say this is the probability wave. So what is oscillating? It is the probability of finding the particle is oscillating. Okay. Now, if you do an experiment, what you will observe is that if you do an experiment, let's say that certain positions, let's say this is position 1, position 2, position 3, position 4, position 5, like this. If you do experiments and put your meter and see whether you will find the particle there or not, maximum number of times it will be found at those locations where there is a maximum, and minimum number of points, or if it is 0, there is almost no time you will find the particle at this minimum. Okay, so I am actually, based on these observations, I am saying that a probability is what is oscillating, and hence I am going to call it as a probability wave. Okay. Now, why this probability wave, or what happens to the particle so that this is what is the situation? Okay, so there one can think of several things. Let's say you have a particle. What is the picture of particle in mind that we have? This is what we think in classical mechanics. Correct?
Localized in space. Point.
Localized in space. But in quantum mechanics, people may say that this is what it is. Okay. Now, how do I call this a particle? What is this wiggly particle? Okay, particle cannot be like this, right? Is it a string or what? Okay, so this looks like a string representation of a particle, right? So what they are trying to plot here, or what is this quantity, is essentially it's a representation of variation of probability. Okay, even though this is a probability, if you look at probability, then it looks something like this. So wherever up is there, that will also up. So something like this it goes. Correct?
Yes.
So
Yes, sir.
this is what is probability. So what is physically this means is that we don't know where the particle is. We know that particle is anywhere between this and this. And there also particle is more likely to be here, here, here than here, here, here. Okay, so that means we don't know where it is. It can be anywhere between them. Means it should be uniform probability, right?
Yes, sir. Yes, sir.
We know something better than that. That's what it means. If you know the wave function, we know something better than saying that I don't know where it is.
Yes, sir.
I know at these locations it is likely to be there. Okay, so that kind of information is what we get experimentally, and that is what makes us to say that it is a kind of a probability wave. This is exactly same as our experiment of polarization. So I have a polarization experiment we discussed, right? I have photons of this polarization state, and I have a polarizer like this. Okay, so I have a polarizer like this. Then I don't know what is going to happen at this point. What is going to the polarization state? What is going to happen to this polarized photon when it passes? I don't know. Okay, but what I know is that the particles which are coming out are n cos square theta. So from there, what I understand is that probability of transmission is equal to cos square theta. How I derived this one, or how I assigned a probability like this, is what I am assigning from the experiment. I am going to assign this quantity. Okay, how I assigned cos square theta here, I am going to assign probability density here. Is that clear? So that experiment, and from the experimental experience, I am now getting probability density. Now, how do I go from probability density to probability? Probability density to probability amplitude. Because you remember our experiment with polarized photons. If I put another polarizer like this will come 100%. Correct? So that means this component, if this was alone there on this side, everything would have come. Everything did not come means this particular fellow has a component like this. And then we discussed that we can write this one as some cos theta times this one plus sine theta times this one, because it could come with this probability. It doesn't come with this probability. When it doesn't come, when the polarization is perpendicular to this, it doesn't come. Correct? So from that I wrote like this. But then to say that it should be square root of probability, we had argued that there are many input states for which you can get n cos square theta. Okay, there are many input states for which you get n cos square theta. And one way to understand how they are different is to have a relative phase between them. Okay, and that relative phase will come only when you take square root of probability, and that is how we fixed this one. In the same way, if you look at an experiment like this, okay, suppose you look at an experiment like this. Let's say you have a source, and then you have a double slit experiment, and then you have a screen. What you observe in quantum mechanics is an interference pattern. Okay. Now, you don't understand this interference pattern if you just work with probabilities. So let us say this is, so let's say that this particular, any particle which is coming to this slit has got psi1 as its wave function. This slit has got psi2 as the wave function. And now at any point on the screen, you would like to find out what is the wave function at this point. It is psi1 plus psi2. When you ask what is the probability there, it is psi1 square plus psi2 square, which is basically psi1 square mod plus psi2 square mod plus 2 times real part of psi1 psi2 star. Okay, it is because of this term that you get interference. Okay, so that means why this is happening? Because it is probability amplitudes that are combining, not the probabilities. If the probabilities are combining, it is this that will be the total probability. Now the total probability is individual probabilities plus an interference term, which comes because we are using what are called the probability density, probability amplitudes, not the probability. Okay, so that is how. So what I am trying to say here is all the experimental experience which went into this postulate. Okay.
Sir.
Okay. Yeah. Yeah. Go ahead.
Sir, in psi of r comma t, r and t are real, but psi is complex. You said no, sir. I could not understand that one, sir.
Yeah. So see, r and t are what? R is a space variable, t is a time variable, right? So they are always real, right? So let's say you have got a coordinate system, and then you have a point r here, and this is your r, right? This is a point. Now you may have some particle here, correct? This is r, and there is a time t, right? So this particle will have a state which is basically psi of r comma. Okay, so this can be r and t are real only, but psi should not be real. That's what it is. What does that mean? Suppose let's say I have so my psi of r comma t can be, let's say, x y z cos omega t maybe plus I x square y sin omega t. So it should have a real part and it should have an imaginary part. But each one of them is only real. X is real, y is real, z is real, t is real. But this one has two parts. That means your psi of rt is not one function, but it is two functions. One thing I will call it as psi real of r comma t plus I times psi imaginary of r comma t. So whenever I say psi complex value, that means when I say one function, I talk about two functions. These two are real functions, but the total function psi of rt is a complex function. Or equivalently, I can write this as, you can say there is some r of r comma t into e to the power is of r comma. In the polar representation, one is a modulus function and a phase function. So I could have, anyway, here also I have two functions, here also I have two functions. So one complex valued function is equivalent to two real valued functions. Is that clear? R and T are real.
Yes, sir. Sir, another doubt that is the photon is acting as both and the electron also acting as both particle and wave vehicle. when we are seeing means that when photon is striking on it is acting as a particle, and again it is coming as a wave I have here. But how and what makes it to happen like that? What is the machinery behind it, sir?
Okay, so let me just look at this experiment carefully. So let's look at this double slit experiment carefully. Okay, maybe just give me a minute. I just wanted to. Okay, so let's go. Okay, so I just wanted to discuss this experiment carefully. So you see this double slit experiment. First, if we are considering bullets, then these bullets will go through one slit or the other. Then you will see there are only two peaks. That means most of the bullets will come according to slit 1 or according to slit 2. If they are passing through slit 1, then they will get collected here. If they are passing through slit 2, they will get collected here. On the other hand, if you do this experiment with water waves, then you know the secondary waves will start at each slit, and those waves will constructively, destructively interfere, and you will get an interference pattern. Now, if you do the same experiment with electrons, okay, so electrons, and you are going to pass these electrons one by one, then you will see that even the electrons will exhibit interference pattern. Okay, so this is what was an experimental evidence for the interference of the electrons. Now, there was an experiment done by someone in Hitachi group, and this experiment is actually one electron will pass through the double slit arrangement. That electron will go and get detected on the screen. Only then the second electron will be injected. So if you see that these electrons I'm just going to play this movie. You can see that how these electrons now you can see that these electrons will be detected. Okay, so have you seen it? Do you want me to play again?
Yes, sir.
You want to see it again, or shall we close it?
We shall close, sir.
Okay. Okay. Yeah.
With less electrons, we could not recognize the pattern, or what? Means like if
Yes.
you
Yes, we could not recognize the pattern. But so two things. One is, let's imagine what happened on the screen. Let's say this is the screen. Okay, so this experiment was done in 95 or something. So first electron comes, you will see a click here. What does that mean? The electron got deposited there. Deposited there means what? It is localized, correct? It is there. Now second electron, let's say it has come here. Okay, so it is there. Third electron has come here. So if you see initially, these electrons are deposited everywhere on the screen. That is why it appeared that you are going to get a uniform distribution. But then, as you send more and more electrons, you will see that there are well-defined regions at which they are appearing, and well-defined regions where they are not appearing. Correct? So there are bright and dark fringes. That means these electrons are coming here, but not in the regions, right? That is what this experiment shows. Okay, so now what can we conclude from this? So these are interference fringes. These are interference fringes. That implies wave nature is responsible. There is no other explanation that I can think of. Since there is an interference, I infer that it is the wave nature that is giving rise to this interference. But each electron is detected on the screen on the screen at a point. What does that mean? That implies it is like a particle. It is like a particle. Okay. Now, prior to this, we know, for example, if you look at Davis and Germer experiment, what happens in Davis and Germer experiment? Electrons diffract. Electron diffraction. Diffraction happens only for waves. So from this, the wave nature is confirmed. Okay. Or if you take Wilson's cloud chamber experiment, Wilson's cloud chamber. Then what is this news, is it? Okay. Now electrons track. What is track? Track is the path is seen. What does that mean? That tells you the particle nature. Okay, so in this experiment, we say that wave nature is manifesting. In this experiment, we say that the particle nature is manifesting. Now, what is happening in this double slit experiment is that we seem to have both natures manifesting in this experiment. Okay, so if there is no wave nature, then there is no interference. But if it's not a particle, then we cannot detect it as a particle. Okay, so what is happening here? Okay, so but this is an experimental observation, right? We cannot deny that. Okay, so maybe we are. So is it correct to say that let's say I have a source here, and there is a double slit arrangement here, and there is a screen here. Okay, so when an electron is coming, so electron, when it crosses double slit, it exhibits wave nature, but when it is detected on the screen, it exhibits particle nature. Is it correct to say like this? That means we have a situation where within one experiment itself, in a part of the experiment, it behaves like a wave, and a part of the experiment, it behaves like a particle.
Sir, when we keep a candle near that one, whether it will come as a wave like that pattern or that a bullet like pattern, sir?
See, that light is an electromagnetic wave, right? So if you put a candle, you should get interference pattern.
No,
But
sir. The electron is coming in that from the source, sir. If you are keeping light near the screen, means what will happen, sir? Whether it will come as a particle like pattern, sir.
why are you putting candle near the screen? What is the purpose? Candle near the screen. What is the purpose?
When the light strike on the electron, it will become as a particle. It will behave as a particle here, sir.
Yeah, but in this particular
Yeah, but-
experiment, there is no such candle, because the screen is a kind of scintillating screen where when an electron comes, you will see a click on that. Okay, or imagine that you are keeping a set of detectors there. When electron goes and gets detected, one detector will show response.
Sir?
Yeah.
I think he wants to ask what will happen if I try to detect the electron in between slit and screen.
Okay, so if that is the question, then the answer is you will not see the interference. Interference will be destroyed. If you want to interact with the electron in between and try to see where it is going, you want to probe in which path it is taking, etc., then the interference will be lost.
Yeah, sir. At that time, my question is, at that time, why it is getting lost? What makes that nature of the electron when the photon comes to change as a particle?
Yeah, that's a good question. That's a good question. We will discuss that question. But the observation is that the interference will be destroyed. Okay, so why is it getting destroyed is a good question. We will come to that. But first, let us settle this issue of dual nature. Okay, so now first question is, here I am making a hypothesis that electron, when it comes crosses double slit, it exhibits wave nature, but when it is detected on the screen, it exhibits particle nature. Is it a correct hypothesis, or is it a valid hypothesis to make? Okay, so what is the justification for this hypothesis? Okay, so let me say that my justification is something like this. Okay, my justification is, now the particle is, so what is the particle? An electron. So electron is some object which I don't know, but this object is something like this. Okay, so we don't know, since we are seeing this many times in many books, let us say we assume this is the electron. Now there is some kind of a length over which this electron has certain non-zero probability, right? Okay, so let us call this as some lambda. Now we can ask a question: if this electron is interacting with, okay, so in one case, case 1, this electron interacts with an apparatus whose length scale is L, which is of the order of, let me call this as capital L, which is of the order of 100 lambda, much bigger than that. That means my apparatus length scale is something like this. So this is my L. In this, where is the particle? It is like this. So do you consider this to be a localized thing? But the electron is this only. But when you look at the scale of capital L, this lambda looks very, very small, right? So this looks like a particle. Okay, so electron is localized. That's what I would infer, right? Electron is localized. I would infer this. And this is what I would interpret as a particle nature. But is electron different? No, electron is same as what I have drawn here. But it looks as if this variation in the length scale of lambda is unimportant when I am looking at the scale of L. Okay. On the other hand, let us look at a situation where second case 2, where electron interacts with an apparatus whose length scale is, let's say, called small l, is of the order of 0.1 lambda. It is much smaller than lambda. So that means my small l is something like this, small l. Then what is capital L? This lambda is something like this. So what happens? This variation is important because I am only seeing here this much, right? So this is only small. So this variation is important, right? So what do I say? Within this thing, I would say that electron is delocalized. Electron is extended or delocalized. And I would interpret this as wave nature. But is electron really changing its nature? It is same. The way I am probing the electron with my different apparatus reveals sometimes its wave nature, sometimes its particle nature. Okay, so this is the justification for me to say when the electron is passing through double slit arrangement, it is like case 2. When the electron is getting detected on the screen, it is like case 1. Okay. Now, I have given a hypothesis and I have given my justification for the hypothesis. Okay. Now, I also have another logic. Okay, so this is the justification, and my justification also comes from the experience in optics. Okay, so in optics, we have something called geometrical optics and wave optics. Yes.
Sir, so you are saying this wave nature and particle nature is just because of resolution. It's nothing inherent.
Yeah, that's what I'm saying. There is nothing inherently that is changing about the electron. Electron is as such, whatever it is. Okay, so how we are interacting with the electron will bring out either particle nature or wave nature depending on our length scales. Okay. Now in geometrical optics, what happens? Geometrical optics, we say that light travels in straight line, right? Rectilinear propagation of light. So how do we do it? We say, okay, there is a lens like this, and then there is a source of light, so it goes like this. Like this we draw ray diagrams, right? So this will go like this kind of ray diagrams, all straight line with scale, right? But now the lens is such a big object compared to the wavelength, this approximation is fine. But now if you take a slit like this, single slit, double slit like that, then the slit width is so small, then you have to actually do wave mechanics. So that will give you a diffraction, interference, those kind of things. So a similar thing is what I am expecting will be happening here. So my justification for saying this is that, so the wave mechanics or wave optics is what wave nature of this particle is, and geometrical optics represents whatever particle nature that exhibits in these particles for these quantum systems.
So,
okay, so yeah.
So what if L is exactly equal to lambda?
If it see, if they exactly equal to lambda or of the order of lambda, then also you will see wave nature, right? If it is much smaller, or if it is of the order of lambda, when do you don't see wave nature is when L is much larger than lambda, you don't see wave nature. Even sometimes if it is 10 times lambda also, you will see wave nature. Correct? But particle nature will be seen when, see, imagine you have a cloud chamber. You know what is the size of the cloud chamber? Cloud chamber sometimes will be so big, right? Sometimes the whole room will be occupied by the cloud chamber, and in that you have this water vapor, and now if an electron is passing through that, you will see a track. That is because the volume occupied by the steam or the water vapor is so huge compared to the whatever lambda of the electron, so it always will be detected as a particle. Now what happens in Davison-Germer experiment? Electrons are impinged on some nickel crystal. Now nickel lattice parameter between nickel atoms in the nickel crystal is so small that electrons will get diffracted. Right? So that is what I am trying to say, that it is because of the way we interact with this. There is no mystery about this. There is no mystery. It's not that electron is behaving mischievously as many textbooks write. There is nothing like that. Electron is as it is always. It is having some wiggly thing that we are depicting here. We don't know actually this wiggly thing is correct, but it has some oscillations in its probability of existence in space, and those oscillations will manifest as a wave nature when our length scales of interaction is of the order of or smaller than the length scale of that variation, and when it is much larger, that variation is unimportant.
Sir?
Yeah.
When the small L is there at that time, when the photon is striking on this wave function, what will be the change, sir?
You are still talking about using some other photon to interact with electron, is it?
Yes, sir.
Yeah, but that part we will come to. So let us first discuss whether this aspect is clear.
Okay, sir. Thank you, sir.
Okay, I'm not saying that whatever I'm saying is correct. Okay, please don't think that I'm giving you the final answer. I'm only making, see how we do, what we do in science is always we make a hypothesis. And then we have to ask the question, how justified is our hypothesis? Why are we making this hypothesis? Because I am thinking, I'm giving my justification also for this hypothesis. Okay, so now how do I test this hypothesis? Because I have to also test this hypothesis. Okay, I don't know whether this is correct or not. So what is our next job? Our next job is to test this hypothesis. Test. How do I test it?
Dr. Sathyanarayana, some problem with your mic. Maybe
So-
you can disconnect your the audio once and plug out
Hello,
and
can
then
you?
plug in some.
I think now it is clear, sir.
It's clear,
Yes, yes, sir.
but I am losing. I think I lost presentation.
No, there is some. You
Lag
can
is-
I think there is some internet
the
connection.
jack. You can remove the jack once again and put it back. That
Yeah, but
microphone jack.
I am getting some message that
No, that jack you can remove and put once again. Some loose contact or something.
is it better?
Yes, yes.
Yeah, better now.
Okay, so is my presentation seen?
No, I think you will have to share your screen again.
Okay, just a minute.
Sir, another one doubt, sir. That is, electron is always like a wave nature, but when we are seeing in the larger scale, it is looking less a particle for us. And my doubt is, how that wave-like nature is having the mass, sir?
Wave-like nature is having?
No, sir. That is when the small L is there, it is a big big wave is there. But when small capital L is there, there is a small particle like, but there is a wave only for electron. Its nature. But in it is only wave, but it is looking as a particle for us. But how come a wave would have mass, sir? That is my doubt, sir.
Okay. So that is why when I say that it is a wave, what I want you to understand is that this wave itself is only our language. Okay. So you have an understanding that only particles can have a mass and waves cannot have a mass, right? Yes or no? That's what
Yes,
you are
sir.
thinking, right? Yeah. But the point is that your particles, can you see it now, my presentation?
Yes, sir. Yes, sir.
Okay. So it is basically, what do I mean by a wave? So let me tell you what I think. Okay. So, but take my thinking also as not final, because this is my understanding. So what I'm trying to say is that basically I have, let's say, some region. I'm going to call this as lambda. What is the basic thing? Basic thing is I don't know where the particle is. Okay, so this is the basic thing. I don't know where the particle is. Okay. Why I don't know? Why I don't know? If you ask a question, why? intrinsically particle cannot remain at one point. What does this mean? That means the particle is restless. It cannot be there at one point. So it is moving, and it is probably moving so fast. I don't know where it is. Now, what is it that I know? What is it that from the experiments I know? Okay, so I know a few things. I know that it is there in the region whose length is lambda. This I know for sure. I know it is there in this region. Now, what else I know? I also know probability variation of its existence in that region. These two things I know. Now, this knowledge is what is helping me to write down the postulate 1. Now, where this knowledge is conflicting with assigning a mass to the particle. Is there any conflict with assigning a mass to the particle? No, right? Particle can have a mass. Okay, so because of this probability variation, I am interpreting this as a probability wave. And which is what I am calling it as a wave nature. I think there is some problem with my network. It's very slow.
Sir, your voice is breaking.
Yeah, I have some. I think it's a very weak network. Let me see if I can close some programs. I don't have anything open.
Now it is okay, sir.
Yeah. Okay, so this probability wave is what gives me a wave nature. And this wave nature is what gives you interference. Okay, so this is experimentally observed. Interference is what is observed. Now, from experiments that I do on individual systems, okay, and I want to explain interference, this whole thing consistently can be done if I do a postulate 1. Now, we should view this comprehensively. We should not take one particular term called wave nature and then misinterpret this as a wave, and wave should not have a mass. That is not going to help us. Okay, so we should understand what we mean by wave nature. Wave nature is because there is a probability variation. We call it a probability wave. That is the wave nature. Why probability we have to resort to? Because we don't know where the particle is. Why we don't know where the particle is? Because particle is not entitled to stay at a point. Somehow that is the reality of quantum mechanics. Particle cannot get localized. Particle keeps fluctuating here and there. It just runs here and there. It is restless. It is this intrinsic restlessness that is responsible for this wave nature. Okay, so if you understand it like this, there is no conflict.
Sir. Sir, how can we say this wave nature is responsible for interference?
What else? How do you explain interference? Interference is a phenomena that is observed only waves. There's a constructive, destructive overlap will be there, and that is how you get the interference. Otherwise, how do you get the interference?
Sir, but this wave nature is not actually a physical thing, right?
Correct. So see, it's a probability wave. So probability waves will interfere to give you maximum and minimum probabilities. And where maximum probability is there, only particles will go and get deposited, right? So probability interference will become intensity interference in the limit n becoming very large. Exactly like what we did in polarization case. Single photon, you don't know whether it will get transmitted or absorbed. But when you use large number of photons, then you will get n cos square theta of them get transmitted, which is same as I cos square theta in Malus law. It is the same thing here. When n becomes very large, the number of particles will come in different locations is basically the probability variation. And that probability variation for large number of electrons will be same as the intensity variation.
Yes, sir.
Correct. So all these things are very consistent with each other. Okay. So now let's come to that important question that one of you have raised. Okay, I have only 10 minutes, but let me see how much. So now the question that is asked by one of you is that suppose I have a source and I have a double slit experiment arrangement here, and then there is a screen. Now an electron comes. So electron starts from S and reaches the screen. Only then the second electron is released. Okay, so that means at any given time in this apparatus, there is only one electron that is present. Now, what happens to this electron? First possibility that the electron passes through one of the two slits. Electron passes through one of the two slits. Okay. And second, electron passes through both the slits. Single electron, remember. And there is a third possibility, that is electron passes through one of the slits, but We don't know. We don't know which one. Three possibilities are there. Here, that means electron passes through one of the two slits. That means we know it passes through one of the two slits. Here it passes through both the slits. Here it passes through one of the slits only, but we don't know which slit. Okay. Now, if you know that it passes through one of the slits, then we would say it is a particle nature. Okay. If it is a wave, then it passes through both the slits. Okay. And I don't know what to call this. So let us come to this third point a little later. Now we ask a question. Supposing electron is, let us say that this third part is correct. Okay, let's say this third part is correct. We don't know which slit it is, but it is passing through one of the slits. Now, suppose if this electron is passing through this slit and reaching here. Okay, now what you can do, just like somebody said, you send in a photon and this photon gets scattered. Okay, you send in a photon, this photon gets scattered, and from this scattered photon, you get an information that it has passed through this slit. If this is not getting scattered, that means it is passing through the other slit. It has to pass through one of the slits, right? So that means by some suitable experimental arrangement, find out which path or which slit electron goes through. Okay, every time, let's say for every electron, you are going to get which path it is taking. It is going through slit 1 or slit 2. And then look at what happens when you send large number of electrons. Okay, so we can observe, that interference is lost. Interference is destroyed. There is no interference. Interference is destroyed. Okay, this is the observation. Okay, now one question was raised. What happens? Why interference is destroyed? Okay, so what happens? Why interference is destroyed? For this, Heisenberg gave a mechanism which is called as Heisenberg mechanism. Now, what Heisenberg said, or what Heisenberg proposed as a mechanism, is that normally when you say that to detect this electron going through slit 1 or slit 2, you have to interact with some other probe particle. It may be photon or it may be something else. Now, when this probe particle collides with the electron, okay, so the collision is basically not controlled. Collision is an uncontrolled process. But what Heisenberg said is that let us assume that we can control the collision. That means A probe particle which is hitting the electron when it is passing through slit 1, when the scattered particle can actually come out in any direction, right? In a collision, how the momentum is getting transferred, how the particle is going to come, we have no idea. We will not be able to predict. But Heisenberg said, let us say for an argument's sake, we can predict it, or we can arrange it in such a way that the particle is hitting the electron and coming out, let's say, at 90 degrees. That means in every collision, we can say this is how the electron is getting deflected in a predictable manner. So Heisenberg expressed his opinion that if that is the case, then interference will not get destroyed, but interference will get shifted or deteriorated a little. Okay, so maybe according to Heisenberg, if the collision can be controlled, okay, so let's say you have an interference pattern like this. Okay, this is the original pattern. So he assumed that if you say that you have a controlled collision, then this interference might get shifted, but it still may have an interference like this. Okay, so controlled collision. Now Heisenberg said, since the collision is not controlled, for every collision there is a different shifts. Okay, so because this is an overlap of different shifts, finally it will destructively interfere and you have no interference. Okay, so this is how he concluded. So what his idea was that since collision of the probe particle, or let's say if the collision of the probe particle is controlled, the deflection of the path of the detected electron does not destroy the interference, but shifts the pattern. Okay. However, since the collision cannot be controlled, the resulting superposition of different shifted patterns result in destruction of interference. Okay, so this is the Heisenberg mechanism. Much later, this mechanism got some justification. Okay, so much later, maybe in 90s. Okay, so I think 1990s, even later. So there was some experimental justification. Okay, so there was an experiment done by Anton Zeilinger's group. In Vienna, Austria. What they did, they tried to do this experiment. So in mid 90s, I think this carbon 60 molecules were discovered, right? So they were trying to do this experiment with double slit experiment at very low temperature with carbon 60 molecules.
Fullerene, no?
Fullerenes, yes. So they were doing this double slit experiment with C60 molecules. Okay, so when they did this experiment, so first they did not get a good interference pattern. First they got kind of some unclear interference pattern. Okay, it doesn't look like interference, but some peaks here and there are there. But then they realized that they did not select C60 with the same velocity. That C60 molecules were not velocity selected properly. That means each one comes with different velocity. Okay, so they were not velocity selected. That means each one has different velocity. There's a distribution of velocity. Okay, so when they fixed this, okay, so when proper velocity selection was done, they got proper interference pattern. Just like electrons that we have seen, they have got proper interference pattern. So this has given kind of a justification to saying that each velocity is probably shifting it a little bit. And when you have a velocity distributed over different velocities, then it doesn't look like an interference pattern. So maybe Heisenberg was right, because from this experiment, we seem to get kind of a experimental justification for Heisenberg's mechanism. Okay.
Sir, is this interference at a macroscopic level, because this is very big molecule?
Yeah. Okay, it is basically anything can get interference if you can do the experiment at low temperatures, because if you decrease the temperature, then you can give wave nature to anything.
The length scale we need will be large. I mean, thermal de Broglie wavelength will be
Correct.
large.
Correct. Yeah. So you know this relation that lambda is equal to h divided by square root of 2 pi m kBt. So if you go to low temperature, you can increase lambda. Okay, so you want to get 1 meter particles behave like quantum particles, you have to go to 10 power minus 18 Kelvin. That's all. Okay, so this is the story about this one. But then let me just probably today I don't have time, but let me tell you that this Heisenberg mechanism was proved to be wrong. Okay, in the sense the interference is not lost because of this. Okay, that there is a beautiful experiment that was done in 1998, which showed that Heisenberg's mechanism is not tenable. But I'll discuss this experiment in the next class. Okay, I will stop.
Sir?
Ah.
Yes. Sir, like in few class back, that coincident detector, that beam splitter, when there, sir, you should know, we need not to subscribe to any like particular web idea. We can just consider the state approach.
Correct.
So
Correct.
this is also with that we can explain, right?
Yes. Yes. So we will. So I am actually trying to put it in the standard language, but this also we can come back from superposition.
Yes.
Yeah. Any other questions?
Yeah, if questions are not there, shall we close then?
Yeah, we can close.
Okay, Saravana Babu.